Okay, so this is where we finished yesterday, so let me pick up from here. So, going back to slides. Okay, so we talked about the class of problems, called NP. So these are problems that can be solved by non-deterministic Turing machines, or equivalently, these are problems for which a solution can be verified efficiently. So if it's not obvious to you why these two definitions are the same, kind of being able to verify a solution and being solved by a non-deterministic Turing machine, I suggest you think about it at home or maybe discuss it with your tutor, because both definitions are important. One, to sort of motivate this class, kind of from a technical perspective, non-deterministic Turing machines are a well-defined object, and the other is to explain why it's important. Right, so we care about problems where we can easily check the solution. Okay, so problems are NP complete if they're NP hard and also in NP. Right, so these are the problems that capture the essence of NP. Right, so NP hard, every problem in NP can be reduced to them. Okay, and you know from the models of computation course that NP completeness is not just an abstract notion, so there are actual easy to state problems that are NP complete. And satisfiability is one of them. Okay, satisfiability is a problem where you are given a Boolean formula and your goal is to decide whether it has a satisfying cosignment. Okay, and roughly this is how the proof went. Well, encode the computation of non-deterministic Turing machine as a table, and then capture that table by a formula with some blanks left in, variables left in for non-deterministic choices. So if there are non-deterministic choices that lead to accepting computation, then there is a setting of your variables that satisfy the formula and vice versa. Okay, so SAT is NP complete, and SAT, of course, is a easy to state, nice enough problem, a problem involving a logical formula. But you know, the problems you have to solve often are not problems about logical formulas. So they're often problems about graphs. So there may be problems about scheduling, there may be problems about all sorts of things, like aligning biological sequences, kind of finding Nash equilibrium in more general games, you know, all sorts of things that really don't look like logical formulas. So suppose you want to pursue this strategy. I showed you in the slide yesterday, I showed you in the picture from Gary Johnson. You want to show that your problem is NP complete, to explain that it's not your fault that you cannot solve it. Okay, so how are you going to go about that? Well, you can try to use the same strategy as in Cook-Levin. Right? So Cook-Levin established that SAT is NP complete using this outline. Well, so maybe you could try to do the same, encode the computation of non-deterministic Turing machine as a fully-sized table, right? And then try to capture that table by a graph so that, say, vertex cover in that graph corresponds to an accepting computation. Right? And you can try to do that for your scheduling problem or for a Nash equilibrium problem. But that seems awfully difficult to do, right? So this isn't an easy reduction. Writing it out in detail takes a good 8 to 10 pages of Sipser's textbook, I think. And even Sipser doesn't give all the technical details. He waves his hand kind of in some places. Right? And you certainly don't want to do that every time you want to prove that a problem is NP complete. Okay, so what can we do instead? Well, so here's where the notion, okay, so this is my picture with SAT sitting here. So can we put more stuff in here? Can we put more stuff in this space, NP complete? And here is where the notion of reduction becomes useful again. Right? Remember, we can use reductions in a straightforward way. If you have a problem you don't know how to solve, and you reduce it to an easy problem, then by doing so you have solved your problem. Right? And this is how we normally use reductions. Okay, and I don't even have to prove that this works. I think it's intuitively clear. But reductions can be also used in the opposite direction. Right, so here is the use of reduction of opposite direction. Suppose problem A is fully time reducible to problem B, and A is NP hard. The problem you're reducing from is NP hard. Then B is NP hard. So what you're doing here, you take a hard problem to start with, and you reduce it to another problem. So the problem you actually care about here, kind of your problem, kind of the problem that comes from an application, is problem B. Right, so you're trying to determine the complexity of B, and you do it by this procedure. You establish that B is NP hard. So you start with a known kind of NP hard problem, and you reduce it to your problem, right? And thereby you establish that B is NP hard. Right. So this is a crucial theorem, and this is something that I think is fundamental to understand for the entire theory of NP hardness and NP completeness. To show that your problem is hard, you take a known problem and reduce it to your problem. Okay, so let's see the proof. The proof is fairly straightforward, right? So it's just a matter of writing down the definitions. Okay, so we know that A is polytime reducible to B. So let's take the reduction. Let's give it a Greek name, mu. Okay, so what we want to show is that B is NP hard. Right, so this means showing that every problem in NP is polytime reducible to B. Okay, so we don't actually have to do that. So all we have to do is to compose the reduction from C to A and A to B. Right? So let's take an arbitrary problem C in NP. So we have to establish that C can be polytime reduced to B. But we already know that C is polytime reducible to A by some polytime reduction lambda C. Right? And we know that because A is in NP hard. Right, so let's take now this reduction lambda C and compose it with mu. Right, so whenever we take an instance of C, we first apply lambda and then apply mu. Right, so when we do this, we get an instance of B, right, because lambda C of C is an instance of A, mu of that is an instance of B. So both reductions preserve the answer. Yes goes to yes, no goes to no. Right, so this is a valid reduction. It's a polytime reduction because, well, it's running times composition of the two respective polynomials. So it's a polytime reduction. It preserves kind of the answer, yes to yes, no to no. So it's a polytime reduction from C to B. Right, so that's all there is to it. I'm explaining it in painful level of detail because it's important. Right, not because it's difficult, because it's important. Okay, so pictorially, which is probably even easier. Right, I think proof by picture works better here. Right, so B is your problem. B is your problem you care about. A is the problem that you know is NP hard. Right? And all you have to construct is this mu. Right? Because you know these lambdas exist. Right? So as soon as you establish mu, you can travel from any point in NP to your B. Right? So the game now is to find. Okay. So we already know what can be taken as your A. Right? So we know one NP complete problem, and this is SAT. Right? So the game is. So in the first place, the game is to establish reductions from SAT, kind of two problems of interest, right? And then as soon as we have kind of these new problems of interest, right, we can also use them as our A. So the first thing we are going to do now is to reduce SAT to a specialized version of SAT, kind of. So this is just to give you an example of an easy reduction, and then we are going to reduce SAT to vertex cover. And as soon as we have that, as soon as we know that vertex cover is NP hard, we can reduce kind of vertex cover to other things to show that these other things are NP hard. Right, so each reduction you do, each mu you establish, makes your life easy in the future because now you have enriched your library of things to reduce from. Right, so from now on, B can be used as a basis of your reductions. Okay, so let's see examples. Okay, so SAT, right, so this is a reminder, the Boolean formula in conjunctive normal form. So in variables and clauses are disjunctions of literals, right? So it's a big conjunction of disjunctions of literals. And the question is whether phi is satisfied. Okay, so let's look at a special version of this problem. Right? So special version is a Boolean formula, so it's Boolean formula again in CNF, but each clause now has at most 3 literals. Right? So and the question is whether phi is satisfied. Right? So 3 SAT looks like an easier problem. Right, it's a special case of SAT. So we know that SAT is NP hard. So it's not clear whether 3 SAT is also NP hard, right? Because it seems like an easier problem. To show that it's hard, right? So again, we have to reduce stuff in NP to it. And as we have just argued, we don't have to do it directly. We can just reduce SAT to 3 SAT. Right? So what we are doing here is we're reducing a general problem to its special case. We show that the special case is as hard as the general problem. So or in other words, if we know how to solve the special case, we also know how to solve the general problem. Okay, so let's prove that. Okay, so we're going to prove that it's NP complete, not just NP hard, NP complete, right? And so this means we need to prove 2 things. We need to prove that it's in NP, and we need to prove NP hardness. To show that it's in NP, it suffices to observe that it's a special case of a problem in NP. Right? So if the harder problem is in NP, solvable by non-deterministic Turing machine, then certainly a special case is as well. Or you can observe it directly by saying, well, if you have a candidate solution, if you have formula phi, you can easily check whether it's satisfiable. Right, and to show NP hardness, we'll show reduction from SAT to 3 SAT. From known hard problem to the problem whose status is unknown. Okay, so how do we do that? Well, what we need to do at the mechanical level, we need to take an instance of SAT, instance of our known hard problem, and transform it into an instance of our problem. Right? Okay, so let's start with an arbitrary instance of SAT. Okay, so if that instance of SAT only contains small clauses, clauses of at most 3 literals, then we are good, right? So we are done. Our reduction is just to output the instance we already have. So suppose not. So what can go wrong? Well, if it's not an instance of 3 SAT, it has clauses with 4 more literals. So what do we do with those? Well, suppose I have a clause with at least 4 literals. So let me sort of break off one of these literals. Or rather break off 2 of those. So I can write this clause as X or Y or something else. Right? And this something else is the junction of kind of couple more things. And now let me introduce a new variable. Right? A fresh variable that doesn't occur in my formula. And then I replace my clause with 2 new variables. This one and this one. Okay. So what do I have to prove? I have to prove that, okay, so that's not a full reduction, that's sort of one step of the reduction. Right, so I will repeat these steps until I'm out of clauses with 4 more literals. So let me first explain why this step preserves correctness, and then I'll explain why eventually after a sequence of such steps we'll get to a 3-SAT formula. Okay, why does it preserve correctness? Well, suppose the original formula was satisfiable. Right, so it was satisfiable, meaning the clause C was satisfiable among other things. So how could C be satisfied? Well, you can satisfy X, you can satisfy Y, or you can satisfy something in D. Right, well, okay, so suppose clause C was satisfied by, suppose I had a satisfying assignment for the original instance that satisfied clause C by satisfying one of X and Y. Then for the new formula, I'll have the same assignment, except I set W to false. Right? And then this satisfies the new formula. This thing is satisfied because the old assignment satisfied X or Y. This part is satisfied because I set W to false. Okay? Now, if my old assignment satisfied T, then I'm going to set W to true. And again, my old assignment takes care of this part, right, because T is satisfied, right, and setting W to true takes care of this part. Okay, so something to note. I'm reasoning now in terms of assignments. I'm arguing that yes instance is mapped to yes instance, and I'm arguing this by talking about how a satisfying assignment for this case can be transformed into a satisfying assignment for this case. Right? At the level of actual reduction, I'm not working with satisfying assignments. So the actual reduction doesn't reason about assignments. It takes a clause and replaces with 2 other clauses. Right? So the reduction doesn't work with the assignment. The proof that the reduction works does, the reduction itself doesn't. Okay, so next. Okay, so why is this whole thing? Okay, so the correctness is preserved, kind of by one step, and I do this until I run out of clauses with 4 more literals. So why would that eventually happen? Well, if I had a long clause, right, if I had a clause of length 7, say here, right, so then after this step I have a clause of length 6 here and a clause of length 3 here. Right, so I can sort of define a measure of kind of complexity of my formula, if you will, by saying by how much the clauses in it exceed length 3. Right, and in each step I reduce that measure by 1. Right, so I don't want to make it completely formal, I think it's clear. Right, so we chop off bits of long clauses until we can no longer do it, right, and we can no longer do it exactly when this thing just is a single. Okay, so this is a reduction. It runs in polynomial time because of this argument, right, and at each step satisfiability is preserved. Right, so if original formula was satisfied, then formula at step 1 is satisfied and vice versa. Same from step 1 to step 2. So satisfiability is preserved at each step. Right, and the reduction itself just works with the description of the problem. It doesn't work with assignments. Okay, makes sense? Okay, so I'm probably over-explaining what is a fairly simple thing, but I sort of want to establish kind of all the sort of difficulties one can encounter with reductions. Okay, so we established that a SAT is hard if there is at most 3 variable per clause, so that for various other simplifications for which the problem still remains hard. So for instance, we showed that Okay, set remains hard if each clause has at most 3 literals. It also remains hard if each clause has exactly 3 literals. Right? So, okay, and now you can sort of figure out how the reduction would go. So if you have this instance of 3 set with some very short clauses, like 1 literal, 2 literals, you lengthen them artificially in a way that preserves correctness. Right? So 3 set remains hard if each variable appears at most 3 times. Right, so again you can fix that by sort of introducing copies of variables. Each literal appears at most twice. Even if you require that each clause contains at least 1 literal that is true and at least 1 literal that is false, right, so that no clause is satisfied with all 3 literals being true. Or in fact if you require that each clause contains exactly 1 literal that is true, right, and a bunch of other variants. Right, and all these hardness proofs use similar techniques. Right, so they tweak the formula slightly and establish that the problem remains hard. Right? Okay, so why do I list all that? Well, because sometimes when you try to establish that your problem is hard, you want to reduce not from SAT, and even not from 3 SAT, but from one of the 3 special versions. Okay, why is it helping you? Well, think about what you have to do at a mechanical level when you do a reduction. You take an instance of known hard problem, and you transform it to an instance of your problem. So if this instance you're starting with, the instance of known hard problem, is known to be relatively simple, have nice structure, you know, each variable appears at most 3 times, maybe it's easier for you to design the reduction, right? Because your reduction only has to work for set formulas with this property, right? So it's sometimes useful. So it's useful to have a library of kind of special cases that are as simple as possible while still preserving hardness. Okay, so to illustrate, now we're going to show and that vertex cover, a problem that seems very different from 3 set, is also NP hard. Right, so here we are building the bridge from the world of logical formulas to the world of combinatorial optimization problems. Okay, so vertex cover, to remind you, okay, so this is the problem of covering the edges of a graph with its vertices. You select vertices so that each edge is covered. You have a budget of k. The question is whether you can do it within the budget of k. Okay, so we're going to prove that it's NP complete. Okay, so it's fairly easy to see that it's in NP, right? So this is something you have to show, right? When you say it's NP complete, it's in NP because given a candidate solution you can verify it, right? And the interesting part is the hardness proof. And we're going to reduce from 3 set with exactly 3 variables per clause. Right, so I'm cheating you slightly because I didn't show that this specific version of 3 set is NP hard. I waved my hands around it. But okay, so this is something that is known, something you can find in the literature. This is a known NP hard problem. Okay. So here's how the reduction works. So let me first explain it kind of formally, and then I'm going to illustrate it, and I think kind of proof by picture works pretty well in this case. But let me first formally describe the reduction formula. So suppose I have a formula in variables and clauses. So then I'm going to construct little subgraphs for different parts of different components of that set, instance of set. Right, and then I'm going to connect it together. Right, so these little components are usually called gadgets in the world of NP hardness reductions. So here are my gadgets. For each variable, I'm going to create 2 vertices. I'm going to label them with x and not x, and I'm going to connect them by an edge. Right, this will be my variable gadget. Now each clause contains exactly 3 variables. So this is the special case of 3 set I reduced from. And so for each clause, I create a triangle. I create 3 vertices and connect them into a triangle. And intuitively, kind of the vertices of that triangle correspond to literals in the clause. Okay, so now we have a bunch of variable gadgets, a bunch of edges, and a bunch of triangles. We don't have to connect them. Right? And that's the interesting part. We connect them in a fairly natural way. So we assume that all triangles have numbered vertices like 1, 2, 3, right? And we connect if the ith literal in the respective clause is x, we add an edge between the ith vertex of that triangle and x. So think of vertices of triangle as being labeled with literals. So we connect them to occurrences of those literals in variable gadgets. Right? So x goes to x, not x goes to not x. So there's one more thing we have to do still, kind of to complete the reduction. Right, so okay, so this specifies a graph. So what else do we have to specify? Right, to specify an instance of vertex cover, budget k. Right, and we set k to be equal to 2m plus n. Okay, so what is 2m plus n? We have n variables and m clauses. So 2, okay, so intuitively the target cover size is 2 for each clause and 1 for each variable. Okay, and that completes the reduction. So now let's see an example. So let's say that this is my formula phi. So I have variables x, y, z, t. I construct these variable gadgets. Right, so this is what variable gadgets look like. I construct my clause gadgets for each of the 3 clauses, and I label them according to the formula. Right, so this is the first clause x, y, z, not x, not y, not t, not x, not z, t. Okay, so now I have to connect them. So let me do it for the first clause. First clause contains all literals occurring positively, x, y, z. Right, so I connect it to x, y, and z. So the second clause contains everything negatively, not x, not y, not t. So I connect to not x, not y, and not t. Right, and the third one is a mixture, so I connect in this fashion. Okay, and my budget, my vertex cover budget is 2m plus n. So in this case it's k. 2 times 3 plus 4. In this case it's 10. Okay, so something to note here. Okay, so let me first say it in words and then show it to you in slides. Okay, so what is 2m plus n? Let me actually move those edges for now. Let me just look at these gadgets. Suppose I have this instance of vertex cover. Vertex cover you can consider for disconnected graphs as well. How many vertices at the bare minimum do I need to cover it? So I need 1 for each variable gadget, right, to cover those edges. And for each triangle I need 2 vertices, right, because it's a triangle, it has 3 edges. So even just to cover those edges, so forget about the edges in between, even just to cover those, I absolutely need n plus 2m. Right? So this is my budget. Right? So I want to cover this very frugally. Right? So my budget is n plus m, meaning in any cover there are going to be 2 vertices kind of in each triangle, any 2 vertices in each triangle. In any cover there is going to be 1 vertex per variable gadget. Right? And everything else should be covered by magic. Right? So everything else should be covered for free. Right? And what I'm going to establish is that everything else can be covered for free exactly if my formula is satisfiable. If it's satisfiable, I can choose kind of which of the vertices here to select and which 2 of the vertices here to select, exactly so that all intermediate edges are covered. Okay, so vertex cover has to be, so the option is vertex cover has to be of the form 2 vertices in each triangle, 1 vertex in each variable gadget. And now the game is to figure out which 2 vertices to choose in each triangle, which 1 vertex to choose in each variable gadget. Right? Okay, and it has to be connected somehow to the satisfiability of phi. Okay, makes sense so far? Okay, so let me do the sort of easy, well, both directions are not very difficult, but let me first go from satisfying assignment to cover. So suppose I have a satisfying assignment. Okay. So again, so note what I'm doing now. So I completed the description of the reduction. What I'm doing now, I'm proving that the reduction is correct. And when I'm proving that, I can reason about assignments. I don't reason about the assignment to construct the graph. I'm reasoning about assignments to show that if a satisfying assignment exists, then a vertex cover exists. Okay, so suppose a satisfying assignment exists, right? In this case, it's true, right? So let me take that satisfying assignment. I have many actually. This formula is pretty easy to satisfy. So let me take this one. X, Z, and T are true, Y is false. Okay, so then kind of that satisfying assignment is very easy to map on the nodes up there, right? So I can I select X because it's set to true. I select Y because it's set to false. So kind of at the upper level, I select kind of exactly what the assignment tells me to select. X, not Y, Z, and T. Okay, so what about the triangles? Well, I know that this is a satisfying assignment. So in each clause, at least 1 variable is true. So maybe more, but at least 1 variable is true. And therefore, at most 2 variables are false. So therefore, in each triangle, I'm going to select 2 vertices, and I'm going to select all false vertices, and possibly some true ones. So I'm going to select 2 per triangle, including all false ones. Okay, so for instance here, so what can I do here? X, Y, Z. So I know that I have to select Y, and I can select one of X and Z. I don't care which one. So let me see what I did in PowerPoint. So I did Y and Z. Right, so I select those 2. I could have done Y and X. Right, so here, not X, not Y, not T. So here I know that not X is false because I selected X, not T is false, so I have to select not X and not T. Right, and here I have to select not X and not Z. Okay, so this is a selection of vertices. I claim that this is actually a vertex cover. Why? Okay, so it's of the required form. It selects kind of 1 node per variable gadget, 2 nodes per triangle. So all such edges are covered. So I have to cover about edges between those 2 parts. Okay, now all edges that are incident on a blue node in a triangle, right? So those are covered because these nodes are covered. These nodes are selected. Right? So everything that starts from a blue node is covered. So I only have to worry about things that start from a white node. Right? So I have to worry about edges like that. Right? So the unselected X. But now what do we know about such edges, unselected? What do we know about such vertices? Right? So these vertices correspond to variables that are true. Right? And they're connected to the representatives in the gadget, which are set to 2. Right? So this X is connected to that X. And that X is selected because we selected variables that are true in our assignment. Therefore, this edge from this X to that X is covered from the other side. Right? So it's covered by that appearance of X. Right? And therefore, everything incident on all edges incident on this triangle are covered. The edges incident on Y and Z are covered because Y and Z are selected. The edge incident on X, the true variable, is covered because the variable is true and therefore the other endpoint is selected. Okay, and therefore everything, all edges are covered. If we had a satisfying assignment, then this vertex cover, constructed on the basis of that satisfying assignment, right, is actually a valid vertex cover. Everything is covered. Make sense? Okay. So now we have to go in the opposite direction. Okay, so what we argued now is that our reduction maps yes instances of satisfying assignment, yes instances of SAT, to yes instances of vertex cover. Now we have to go in the opposite direction to show that no instance of satisfying assignment are mapped to no instance of vertex cover. So if we started with a formula that was not satisfiable, there is no way we can get a vertex cover. It's usually more convenient to prove a contrapositive, right? To prove that if there is a cover of size k, then there is a satisfying assignment. Okay, and this is sort of slightly tricky argument usually. So suppose there is a vertex cover, right? So we want to extract from that cover a satisfying assignment for my formula. Okay, so this is the graph. We have a vertex cover for it. Okay, so what do we know about vertex covers? Kind of in graphs of this form. So we know that kind of to even have a chance of being a vertex cover of that size, right? So this set of vertices should contain 1 vertex in each variable gadget and 2 vertices in each triangle, because it has to cover edges like that and it has to cover triangle edges. Right? So at least it's something of this shape. Right? So we know something about its shape. Right? So in particular, its shape suggests to us a potential satisfying assignment. Right? So we can read off the assignment from the top level. Right? And the assignment we read of this particular vertex cover would be X to true, Y to false, Z to true, T to true. Because exactly in the variable gadget, in each variable gadget, exactly 1 node is selected, and that suggests a particular satisfying assignment. Okay, so now why is this satisfying assignment? Why is this actually a satisfying assignment? It's just an assignment. Why is it a satisfying assignment? We know that we have a vertex cover, and from that we have to derive that this assignment constructed from it is a satisfying assignment. Okay, why is that? Well, let's look at a specific clause. Okay, so this is let's look at a specific clause. Say this one. Well, so this clause corresponds to a triangle. Let's maybe look at this one. This one is more interesting. Right, so this clause corresponds to a triangle. We have to argue that this clause is satisfied. We have to argue that each clause is satisfied. Okay, so we know that kind of everything that touches this triangle is covered. Now this triangle has two nodes selected and one node unselected. Right, because our vertex cover is of size k, it has to select exactly two nodes per triangle. Right, so it selects two things, right, and it doesn't select one thing. Right, but we know that we started with a vertex cover. Right, so this one, okay, so the two things that are selected, okay, so these, okay, I want to say it correctly. Okay, so we look at this clause, we know that this clause contains one node that is not in the vertex cover. That one node corresponds to a particular truth value for a variable. Right, so this one node corresponds to y being false. Right, and I want to argue that this means that this clause is satisfied, and it's satisfied by virtue of y being false. Well, why is that? Well, we know that the edge that touches y is covered, because we start with a vertex cover. Therefore, the edge from y goes to a selected node. This means that in our assignment, we set y to false. Right? So this edge being covered means this edge goes to a blue node. Right? And the blue node here tells us to set y to false. Right? And if y is set to false, right? So this means that y is false means that this clause is satisfied. Right? So for each triangle, we pick an uncovered node. We look at the value in that node, right? And this is x, not y, and t. And we claim that this value is actually the literal that satisfies this node. Right? So this clause is satisfied because it contains literal x. This clause is satisfied because it contains literal not y. This clause is satisfied because it contains literal t. Right? And why is that literal true? Again, well, that literal is true because the edge adjacent to that node in the triangle is covered. Right? If it's covered, it cannot be covered from this side, so it's covered from the other side, and that it being covered from the other side means that we, in our assignment, we selected y to be false. Yeah, question?
What happens if you've got, say, both nodes in a variable thing covered?
I cannot, because I know that I have my vertex. My vertex cover is of specific size. I know that it's a vertex cover and it's of a size that doesn't afford kind of me the option of selecting two nodes here. Right? This is why it had to be of that size. Right? So it's all very cleverly tuned in the original reduction to rule that out. Right? And so that's a good question. So it illustrates a general difficulty with NP hardness reductions. Right, so it's often kind of easy to set things up so that yes instance of the original problem maps onto the yes instance of the known problem. Right, so you have a satisfying assignment and it immediately suggests the vertex cover. Right, but when you look at the vertex cover of this graph, potentially, if we're not as careful as we were, it could be that, this vertex cover is all over the place. Right, so in some triangle it selects 3 nodes. Right, in some triangle it selects 1 node. Right? So we know that the vertex cover is of this convenient shape because it's a small vertex cover. It's vertex cover of exactly the right size. Right? And this is why this reduction works. Okay, so something else to note about this reduction. So we proved that vertex cover is NP hard. Right? So we proved that vertex cover is hard for general graphs. Right? So again, at a high level, if you knew how to solve vertex cover, you could do this reduction from SAT to vertex cover. Right? And if you could solve vertex cover here, you could build satisfying assignments from SAT. Right? So if vertex cover were easy, hypothetically, then SAT would be easy. Right? And in fact, yeah, so we proved something stronger. We actually established a formal, what's called many-to-one reduction. Okay, so vertex cover is hard for general graphs. I claim that vertex cover is also hard for graphs of degree at most 3. Why is that? It's because our reduction actually constructed of degree at most. No, wait. I shouldn't be saying that. No, I don't have that yet. Okay, so sorry, I don't have that claim of degree at most 3. Yeah, so maybe I can maybe I can make some other claim of that sort. Okay. Let's see. So I can probably. Okay, so here's what I wanted to say. I wanted to say that this reduction constructs graphs of the degree of each vertex is at most 3, and this is certainly true in this picture. This is not true in general, because to prove that this is true in general, I would have to argue that these degrees are small, right? And this y potentially can be connected. There can be a lot of different kind of triangles connecting to that y, right? So if there's a lot of occurrences of y, this graph would have high degree. But suppose in my reduction, instead of reducing from kind of regular set with 3 variables per clause, I would reduce from a variant of set where each variable occurs at most 3 times. Right? And I know that this is NP-hard as well. Right? So suppose I consider, instead of reducing from general 3 set with 3 variables per clause, I reduce from set with 3 variables per clause and each variable appearing at most 3 times. Right? And this is also NP-hard. Right? So if I do that, then the graphs I get here would have bounded degree. Right? So why is that? Well, the triangle vertices all uniformly have degree 3, and this y would only have, 3 other y's, triangle y's talking to it, plus its neighbor here, so the degree would be at most 4. Right? So what that actually establishes is that vertex cover remains hard for graphs of degree at most 4. Right? And with a little bit more work, I can show that actually it's true for graphs of degree at most 3. Right? Okay, and that's another way of showing that special case of your problem is NP-hard. Right? So to show that 3 set is hard, we reduce set to 3 set. We took an instance of set and sort of massaged it so that no clause has more than 3 variables. Here I didn't take an instance of vertex cover and massaged it to have a small degree. I just looked at my reduction and said, look, in my reduction, I only get graphs that have this special property. Therefore, my problem remains hard for graphs with this special property. Right? And it's sometimes useful to know. Is your problem still NP-hard if the degree of each vertex is at most 4? Well, yes, by this reduction, sort of this reduction. On the other hand, is vertex cover still hard if your graph has degree at most 2? Well, maybe not. Graphs of degree at most 2 are collections of paths and cycles, right? And it's pretty easy to figure out how to cover them optimally. Right? So you sort of want to know generally, when you deal with the problem, which parts of the problem make it hard. Right? So does reducing degree help? Well, yes, but you have to reduce it very severely. Reducing it just to 4 doesn't help. Right? So does vertex cover remain hard for planar graphs? Right, so this graph is not planar, but again, this reduction can be massaged to make it planar. Right, so vertex cover remains hard for planar graphs. Okay, so I think it's enough talking about vertex cover. So what we want to do now is we want to further enrich our library of NP-hard problems. So in our library, we now have set and a few versions of set. And we have vertex cover, including vertex cover for graphs of degree at most 4. Right, then, okay, so now if we want to prove something to be NP-hard, we can take set and reduce to our problem, or we can take vertex cover to reduce to our problem. Right, but we want to know more problems we can reduce from. So let me give you a couple more examples. Okay, one example is independent set. Independent set is another graph problem where we have an undirected graph and an integer, k, and we ask if there is a subset of vertices so that these vertices form an independent set. Right, so here, for instance, the set of orange vertices is an independent set. Okay, my claim is that independent set is NP-hard. Right, and I'm going to prove that. Okay, so it's NP-complete. So why? So 2 things we need to show. To show that the problem is NP-complete, first we have to show that it's in NP, and that's typically easy. So in this case, it's easy because given a set of vertices, we can easily check that there are no edges between elements of this set. There are no edges. Right. So now we have to prove that it's NP-hard. And I'm going to reduce from vertex cover. And this reduction is going to be very, very simple. Right. The reduction relies on the fact that if a set of vertices forms a vertex cover, then its complement forms an independent set. Okay, why is that? Well, let's look at this picture. So the yellow set forms a vertex cover, meaning yellow set covers all edges. each edge has at least one yellow endpoint. Therefore, no edge has two orange endpoints. Therefore, no edge goes between two orange points. Therefore, the orange set is independent. Right? So conversely, okay, so complement of a vertex cover is an independent set. Conversely, a complement of an independent set is a vertex cover. Well, if orange is an independent set, then no edge goes between two orange vertices. Therefore, every edge has at least one yellow endpoint. Right? Therefore, every edge is covered by yellow. Right? So I have that. Okay, so this is a fact. This is a graph theoretic fact. And this elementary graph theoretic fact gives me a reduction. Right? And the reduction maps an instance of vertex cover to an instance of independent set by taking exactly the same graph and flipping the value of k. Okay, why does that work? Well, if G has a vertex cover of size k, then its complement, which is of size b minus k, is an independent set. So yes instance goes to yes instance, and no instance goes to no instance, which we prove by contrapositive. If we have a yes instance here, right, therefore we have an independent set of size b minus k, therefore its complement of size k is a vertex cover. If we have a yes instance here, therefore we started with a yes instance there. Okay, so as far as reductions go, right, so that's about as easy as it gets. We didn't even have to touch the graph, right, but it's a valid reduction. Okay, so now, okay, trick question. Suppose you believe my claim that vertex cover remains hard on graphs of degree at most 4. Can you say the same about independent set? Okay, yes, no, some answers. I know that it's hard to solve vertex cover on graphs G of degree at most 4. Does the same hold true for independent set? Okay, I think I'll have to ask for a show of hands. How many people think that the answer is yes? Okay, how many people believe the answer is no? Okay, some as well. Okay, so let me do the argument. So yes, it actually remains NP hard, because in this reduction, nothing happens to this graph. Right? So the problem, a vertex cover is hard when G has bounded degree. Right? In this reduction, I construct the graph of bounded degree, namely the same graph G, I don't touch it. Right? So the resulting instance kind of is a graph of bounded degree. Right? So therefore, independent set remains hard for graphs of bounded degree. Okay. So I'm going to ask a variant of the same question in a couple of minutes. Okay, so here's another NP hard problem. Click. So click, okay, so you know what a click in a graph is. It's a subset of vertices that is fully connected. So there's an edge between every pair of points, right? And we're looking for large clicks. Small clicks are easy, clicks of size 1 are easy, right? So large clicks are kind of what is interesting here. Right, and we ask whether click is NP complete. Right, and this reduction is not very difficult either. Right, so we are going to reduce from independent set now. Okay, we just enriched our library of NP hard problems. Now we have independent set. We can reduce from independent set. Right, and this time instead of flipping k, we flip the graph. Right, so I'm reducing from independent set. I have to construct an instance of click. Right, and in my instance of click, the graph is a graph on the same set of vertices, but the set of edges is exactly the complement. I include an edge if and only if it did not appear in the original graph. Right? And I keep k the same. And now the claim is, so now the graph theoretic claim. So a set of vertices forms a click in the new graph if and only if it formed an independent set in the original graph. Which is sort of by definition. Right? So all edges are present between vertices in S, exactly if all these edges were absent in the original graph. Okay. So my reduction is map G to this flipped G to its complement and keep k the same. Right? So an instance of independent set is mapped to an instance of click. Right? So again, things to look out for. The reduction goes from a known hard problem do the problem we are trying to establish to be hard. Right? So as we do the reduction, we don't talk about actual clicks or independent sets. So the reduction maps input graph to a different graph, right? And to argue correctness, we actually reason about independent sets and clicks. Right, so the argument now is, if there was an independent set of size k here, there's an independent set of size k here, there's a click of size k here, and it's exactly the same set of vertices. Conversely, right, if there is a click of size k here, there was an independent set of size k here, and that was the same set. Okay, so now repeating the question. We know that independent set remains hard for graphs of degree at most 4. Is the same true for click? Yes, no, no. Right? Because here we flip the graph. Right? So the graph is no longer the same. So in fact, if this was a low degree graph, now it's a high degree graph. Right? And also intuitively, it should be intuitively obvious that click is easy for low degree graphs. Right? So if your graph has degree at most 4, right? So it cannot contain a click of size more than 5. Right, and so the maximum size of click you can hope for is 5, right? So if in your instance you have k bigger than 5, you can immediately answer no, it's not going to contain a large click, right? And if you ask about smaller k, you can go over all sets of vertices of size at most 5, right? So the roughly n to the 5 of such sets of vertices, which is polynomial. You can check for each of them whether it actually forms a click, right? So click is definitely easier on graphs of bounded degree. Independent set isn't. Okay, so these were some examples of NP hardness reductions, right? So again, things to watch for: what we reduce from, what we reduce to, how do we prove correctness, right? So the reduction goes in one direction, you prove a known hard problem, you reduce a known hard problem to your problem. The proof of correctness goes in two directions. Yes instances map to yes instances, no instances map to no instances. This sometimes confuses people. Sometimes people ask, shouldn't we reduce also, say, click to independent set? Shouldn't we reduce vertex cover to set? No, the answer is no. Right, so what we did in class, when we argued no instances map to no instances, we didn't reduce vertex cover to set. What we did is we argued that no instances map to no instances. Right, so we argued that the reduction is actually a correct reduction. So just one reduction in one direction, but for correctness we have to argue two things. Yes instances to yes instances, no instances to no instances. So I think, unlike in previous years, we'll probably spend the entire next lecture looking at more examples of NP hard problems, right? Because I think it's useful to have a larger library of those. Okay, so that's the plan for the first lecture of next week. That's all. So, and by the way, so I updated yesterday's slides kind of to fix a couple of bugs that we noticed there. Right, so generally I try to update slides when we find bugs in the lecture. Yes, so apologies, I got it wrong last week. Yes, it's entirely my fault. So somehow I posted the solution for this video on Friday and forgot to post it. So my intention is always to post it on Friday. Thank you so much. Okay, so basically, so I think if you complain to me as soon as you can find the sheet, so in the future, right? Okay, so sorry about that.
I asked him if she wants to go with me, and otherwise then we'll go like for free.
Well, I'll send you alongside the machine. Yeah,
really early up last night. I literally thought about it, but it'll be very cool to do that.
When think I work. Well, I can't do Monday because we'll do for the next Sunday, so Sunday 8. If you wanted to come, because that's just really friends.